Welcome. In this lecture, we're going to look at hinge loss for design of binary classifiers. So we'll begin by looking at some of the disadvantages of using squared error as a metric for designing classifiers. And that'll lead us to the idea of hinge loss as a cost function for classifier design, and then we'll look at some of the characteristics of the hinge loss cost function. Using squared error as a loss measure when designing a classifier can lead to some problematic results. So let's reformulate the classifier design problem, minimize the combination of some loss function L plus a regularizer term lambda times R of W. Now so far in this course we've been using the squared error loss, which is the 2 norm of AW minus D, where A is a matrix whose rows contain the features of our data, and D represents the labels. So let's take an example where we try to classify planets, whether they're a dwarf planet or an actual planet, and we'll take 3 dwarf planets, Ceres, Eris, and Pluto, and their radius in terms of millions of meters are given in this table here. So we're going to assign a label -1 to the dwarf planets. And then we'll pick 3 real planets, start with a small one, Mercury, one in the middle, Earth, and then Jupiter, a large planet, and we'll give those labels +1. So if we set up our classifier design problem, we'll have a matrix A containing the features, our labels in D, and we solve for our least squares weights, and we find that we get a weight vector that is on the order of 0.01 times 1 and -28. So this leads to the decision boundary. If the radius is less than 28 million meters, then it's going to be a dwarf planet, whereas if the radius is greater than 28 million meters, it's an actual planet. Now the problem here is that Earth gets classified as a dwarf planet, as does Mercury. The use of the squared error as a metric for determining the boundary is what leads to the poor classification. So one of the problems with using squared error is that there's loss associated with easy to classify data. So Jupiter should be very easy to classify, but because it's so much bigger than all the other data points, it ends up contributing to the loss, as we'll see in a moment. But we could take a different approach. We could take something called a max margin classifier, which is going to choose the decision boundary to be the midpoint between the 2 classes. Since they're scalars, it's pretty simple. The decision boundary is the midpoint between the radius of Pluto, which is 2.4 million meters, and Mercury, which is 4.9 million. So that gives us a decision where we're predicting a label d hat as the sine of the radius minus 3.65 million meters. Our margin in this case is the distance between the categories, which is 4.9 minus 2.4. In other words, 2.5 is the class separation. Now we could have chosen a threshold anywhere between 2.4 and 4.9, and we would have correctly made decisions based on this training data. So our data that we actually want to classify at some point could fall in this interval between the two, and by putting the boundary at the midpoint, we are hedging our bets that on average we're going to correctly separate things. Now let's look at the squared error loss in this case. Define the individual elements. My vector D is D sub I and the rows of A as xi transpose, then I can write my squared error loss as a sum from I equals 1 to n di minus xi transpose W quantity squared. And since di is going to be plus or minus 1 in this binary classification problem, I can factor the di out of this expression and rewrite this as 1 minus di times xi transpose W quantity squared. If di has the same sign as xi transpose W, then I'd make a correct decision. So when di times xi transpose W is greater than 0, I make a correct classification. If di has the opposite sign of xi transpose W, then I'm making a misclassification. We can plot this squared error just for one of the i's, and on the axis I'm going to display di xi transpose W. When that's greater than 0, we're making correct decisions. And if you think about this, when this product becomes very large, those should be the easy cases, because that's the case where xi transpose W is a large and positive number and di is +1, in other words, the case of Jupiter. On the other hand, if xi transpose w is a very large negative number and di is all -1, then this product is also going to be a large number, and that again should be an easy thing to classify. However, what we see is that this squared error loss term is quadratic based on the distance that di xi transpose w is from 1. I incur loss when I'm making incorrect decisions over here on the far left, but I also have contributions to my cost function when I have the easy decisions. And that's precisely why Jupiter out here with a very large value pulls our decision boundary far to the right and therefore leads to a significant number of misclassifications in this example. So ideally, what we like to do is count the number of misclassifications and try to optimize that. In other words, minimize the number of misclassifications. Well, we could do that with a loss function that's given by the indicator function applied to di xi transpose w being less than 0. In other words, when this condition is satisfied, the value is 1. When this condition is not satisfied, the value is 0. So that takes the shape of this step. And so for each I, if there's a misclassification, I'm going to have a 1 contributing to the loss and a 0 if there's a correct classification. While that might be ideal, it's very problematic because this is a non-convex function. And when we try to solve for w by optimizing this loss, we're going to run into all sorts of difficulties due to the non-convexity. You can see that it's non-convex because if I draw a line from a point over here to the left of 0 to some point over here on the right of 0, there's a portion of the function that lies above the line. Hinge loss is a way of, to some degree, approximating the ideal loss function, but yet with a convex function. In particular, hinge loss does not introduce loss or penalties to the cost function when the data is easy to classify. So we can define hinge loss as a sum from I equals 1 to n of the quantity 1 minus di xi transpose w, and then we're going to take the positive part of that. So what this operator means when we take the positive part is that if the quantity inside is greater than 0, we just replace it with the quantity itself, and when it's negative, then it's going to be given by 0. So initially, when di times xi transpose w is negative, that corresponds to incorrect decisions over here to the left. And since the sign of di is different than the sign of xi transpose w, this becomes a positive number. And we have this function that has a slope of -1 and goes to 0 then when I hit 1 for di times xi transpose w. Then as di xi transpose w is greater than 1, this difference becomes negative, and my loss in that case goes to 0. So I have this piecewise function that's sketched here in orange. And this prevents cases that are very easy to classify, which have large values of di xi transpose times w, from influencing the design of w, because they contribute 0 to the loss function. So when we're to the right of 1 with di xi transpose w, we have no loss. And then the loss increases as we go to the left of 1. So there is this interval between 0 and 1 for di xi transpose w where we're making correct decisions, but we are incurring some loss. And this is the price we pay for obtaining a convex function. You can see that if I draw a line between any 2 points on this loss function, we're going to stay above the function itself, so this one has the convexity property. Now, interestingly, it's not differentiable due to this joint at 1. So let's consider what this looks like in terms of a classification problem. So I've drawn here is a series of values, the minus signs being labels that were -1 in some two-dimensional plane, the plus symbols representing labels of +1, and then I have my decision boundary, x transpose w equals 0, shown in the green line. Then I have x transpose w equals 1, and x transpose w equals -1, shown on each side of the decision boundary. If x transpose w exceeds 1, in other words, I'm up to the right, and my label is positive, then I have no hinge loss here. okay, because that puts me over in this region. Similarly, if X transpose W is less than or equal to -1, and my label is -1, as shown by these light blue minus signs, then I also have no hinge loss associated with these points, because again, I'm over here in terms of the loss function. Now, when I'm in between these 2 points, I could have the case where X transpose W is indeed positive, but it's less than 1, such as this point right here, and that would put me in this interval between 0 and 1. So there's some small hinge loss associated with this point. Similarly, there'd be a small hinge loss associated with this label of -1. Even though it's correctly classified, again, that's going to be in this interval, it's going to have some loss. Now I have 2 other points that I've illustrated here that have some small hinge loss. This plus here is incorrectly classified because it's below the X transpose W equals 0 line, and that's going to be just in this region to the left here, so the hinge loss is going to be slightly greater than 1 for this point, and similarly for this point here. Now in contrast, the symbols shown in red, if I have a label -1 way up here to the right, that's going to have a fairly large hinge loss because I'm far over here on the left side of the axis. Similarly, with a plus label that has X transpose W much less than -1, then again I'm over here on the left side of the axis and I have a fairly large value for the hinge loss. So hinge loss does a much better job than squared error at approximating the ideal cost function for classification. That is, counting the number of misclassifications. It leads to a convex cost, but that's not one we can solve in closed form. So we'll have to develop some iterative algorithms to find the minimum hinge loss classifier, and we'll do that using the proximal gradient approach that we have previously derived for the least squares loss.